Hello, this is my Physics 2211 Lab 5 Choose Your Own Adventure. The purpose of this lab is to observe the motion of a falling spring with a hanging weight. Then I will create a computational model that predicts the motion of the falling spring and weight. Finally, I will compare the observed and predicted motion. The physics principles used for this lab include forces such as the spring force and the force of gravity. I will also be using Newton's second law alongside the velocity and position update formula. Finally, I will be using the concept of elastic collision, where the initial momentum is equal to the final momentum and where the initial energy is equal to the final energy. The formulas for all of these principles discussed are in the slide you are now seeing. As a preview of the results, we conclude that the computational model predicts the spring's motion accurately. This is a diagram of my experiment. Initially, I am grabbing the spring from the top, and it's at rest. Then I let go of the top and it starts to fall while the bottom continues to be at rest. Finally, the spring gets compressed and it starts falling. Here, the system is the spring and the mass, while the surroundings are everything else. Some assumptions made are that the motion is purely vertical and that there is no air resistance. As seen in the slide, the mass of the spring is 59.2 grams and its initial depth 10.8 centimeters, and its constant was found to be 35.5 newtons per meter. The initial mass of the experiment is 500 grams. This is a video of the spring which reflects the motion described previously. This is because at first only the top moves, yet afterwards, once the bottom and mass start moving, the whole system starts to fall normally. I afterwards used this video on Tracker to get its motion over time. Now, regarding the computational model, I split the system into many ideal massless springs connected in series with point masses where the springs connect. This is because the spring used is not ideal since it has mass, so our usual formulas aren't accurate. Regarding the code of the computational model, I calculated the net force of each of the masses of the system. To do this, I needed to iterate on each of the masses. For all of them, I found their weight, which was found by multiplying their mass times gravity, pointing downwards in the y direction. Then I needed to find the force at the top, which was done by the iterations in the code I greater than 0, which makes it so that as long as the mass is the topmost, the force is simply the spring force found by the formula shown in the code. Then, for all the masses except the bottommost one, the force at the bottom is also the spring force. For the lowest mass, which is found with the else condition, the spring below must use the hanging mass, as there are no more additional small masses below it. After all, I found the net force of the hanging mass, which is found by summing the weight and the force being held on it by the spring on the top. Finally, to generate a loop in the code, I use the position and velocity update formula to constantly update the position and velocity of each of the masses. This is a screenshot of the video of the results of the computational model, where the masses of the spring are slowly getting closer together. This is the graph of the predicted and observed motion of the top and the bottom of the spring. As we can see, the model accurately predicts the observed motion despite being a complex system. The only difference between the motions is at the beginning when the maximum amount of compression is reached. Some sources of errors include possible inaccuracies using Tracker, not using other ways for adding the string in the computational model, and not considering air resistance. The first additional question is, what does it mean? Well, this experiment demonstrates the importance of taking everything into account in the computational model. If we had considered the spring as a simple object, or if we had assumed it was ideal, then our model wouldn't be as accurate. The second additional question is, what if there was no additional mass? If this were the case, then the spring will be less stretched initially. Additionally, the position of the center of mass will be different. So, as a conclusion, we can say that the computational model created predicts fairly well the observed position, especially as time passes. However, the observed and predicted positions diverge at the beginning, which could be explained by aspects like the air resistance which were not considered in this experiment. Thank you for your time.